Okay, this is take 2 on sharing a few problems with you from chapter 13. First time I tried this, I forgot to share my screen, so I was pretty much talking to myself. So the problem I'm going to start with is problem 55 out of chapter 13. It's on page 530. So I will set this up, and the first thing I will do is make sure that I share my screen. Okay, so problem 55 on page 530. It's one where they give you a KP for a reaction. So if you look at the problem, the KP is given, the reaction is given, and they want you to determine the value of KC. The important thing to realize is you can only have a KP if you have all gases for your products and reactants. So we're going to use the ideal gas law to convert from pressure to molarity. So if you take the ideal gas law, you have PV equals nRT. I can take the RT to the left-hand side and the V over to the right-hand side. What I end up with, pressure divided by RT equals molarity. So it equals moles per volume. And if I'm working in the right gas constant units, that'll be moles per liter, which is molarity. So knowing that, I can look at the KP, and if I want to take it to a KC, I have to take each of these pressures and divide it by RT. So the pressure of NO squared has to be divided by RT squared, because the pressure squared. The pressure of Cl2 divided by RT. The pressure of the reactant squared divided by RT squared. And what you end up with, 2 RTs on the top and 2 on the bottom cancel, and you end up with Kc equals Kp times 1 over RT. So this equation that compares the two comes from understanding the relationship between pressure and concentration with the ideal gas law. So if we had equal number of moles on each side, all of the RTs would cancel. But we have 1 extra on the product side, so we end up with 1 over RT extra in this particular case. So I take Kc, I put in the value for Kp, divide by RT in units of liter atmospheres, and the temperature, and I get a Kc of 6.5 times 10 to the minus 8. So we always have to work in pressure units of atmosphere and concentration of molarity. So even though the gas const or the equilibrium constants are unitless, that's a result of where this comes from. And if you take physical chemistry, you'll see that each and every pressure and concentration is divided by a standard state, which may not make a lot of sense. But the important thing is this doesn't have units, but I had to use units of molarity to calculate it. This doesn't have units of pressure, but I had to use atmospheres. I couldn't use millimeters of mercury or something else. So the next problem we're going to look at is 63. So that one is also on page 530. So it's one where we have oxygen diatomic in equilibrium with ozone. So that's 3O2 in equilibrium with 2 moles of O3. And it asks you, if this is the Kc, 1.7 times 10 to the minus 56, do we have much ozone present in our atmosphere in equilibrium with O2? And the answer is no, with an exclamation point. 10 to the minus 56 products over reactant ratio is really small. So the second thing it asks you is just calculate how much ozone we have. So if we have this Kc, and it's going to be equal to, yes, it's Kc, the concentration of ozone squared over the concentration of oxygen cubed. If you solve for ozone, you get a concentration of 9.3 times 10 to the minus 32 molar. So pretty much no ozone is in the lower atmosphere as a result of just oxygen breaking apart and forming ozone. So that's just a problem to think about the size of an equilibrium constant. The next problem is on the next page, so it's 69 on page 531. And let me see. Yeah, so we have a solution, and it's not aqueous, so it says solution instead of aqueous or liquid. So the solvent is carbon tetrachloride, which won't be important, but the important thing is these aren't pure liquids. They're solutions of these things. So you have bromine in solution with carbon tet, chlorine in solution with carbon tet. So when we write the equilibrium constant, it'll be bromine times chlorine divided by the bromochloride squared. And this one asks us first, which way will the reaction go if we mix some stuff up? So our Kc is given to be our 0.145, and they tell us that we mix 0.35, that is the, let me just make sure, the 0.035 is the bromine, the 0.030 is the chlorine, and then the reactant is a concentration of 0.050. So that's what you mix up. So you can calculate a Q by putting bromine times chlorine divided by the bromochloride squared, and I get a QC of 0.42. And then I have to ask the question, which way does the reaction go? Well, if QC is bigger, and it is, than Kc, then the reaction is going to go from left to right. Yes, we are going to form more product in order to reach equilibrium. And so you wouldn't have had to have known which way the reaction goes. It'll just make the math a little easier. But you'll see if we had made the wrong decision about which way it goes, we just get a negative x. And we can talk about that after I solve for x. So now I want to solve for what is the concentration of each of these things when we're at equilibrium. So we have the equilibrium constant, and now I know, oh, why did I say it went the other way? It reacts to the left, yeah, making sense, that it goes this way. So some of the bromine will react, so I'll call that x. The same amount of chlorine will react because the stoichiometric coefficient is the same. But for every one of these that reacts, I get two of these because there's a 2 here. So the equation I have to solve is 0.035 minus x times 0.030 minus x divided by 0.050 plus 2x squared. And I have to solve for x in that equation. So let's just go ahead and jump to Mathematica and solve it in Mathematica, just so we continue to practice that. So in Mathematica, I'm going to say solve, starting with a capital letter and square brackets. And then I'm just going to put this in. So it's going to be 0.035 minus x times 0.030 minus x divided by 0.050 plus 2 times x, and that's going to be squared, so caret 2. And that, remember, you do equal, equal, and it has to equal the equilibrium constant, and I'm solving for x, so comma x. And then you do shift enter. And you get 2 different values. And the first one makes sense, but the second one, if you subtracted 0.216 from 0.035, if you're looking at your problem, you would get a negative number. So that one's not going to work. So x equals the 0.007 757. See if I can make that bigger. Oh, except I forgot to share my screen. So come on. I forgot to share my screen, but not all is lost because, so here's what I put in to Mathematica. I put in 0.035 minus x times 0.030 minus x divided by 0.050 plus 2 times x, and that denominator squared, and then equals 0.145, and I'm solving for x. So now that you can see these two, only one of them makes sense, the first one. The second one would make the concentrations negative when we subtracted it. So that would not make sense. So let's go back. And, okay, so if x equals 0.00757, if I subtract it from this value, that'll be my bromine concentration. So that's the first one. So you can do the math too. And with that subtraction, I only have 2 sig figs. I only have 3 to the right of the decimal, remembering sig figs. So then 0.03 minus 0.00757 gives me chlorine 0.022. And then the bromo chloride, I've got to add 2 times that. So 2 times 0.00757 plus 0.05 gives me 0.065. All of those have units of molarity. So you should get used to using Mathematica unless you prefer to use your calculator, but a lot of problems are just going to be complex. Some will be quadratics, some will be cubics, but Mathematica will be accessible to you on your tests. Okay, so the next problem is 89, and it is on page 532. So it gives you this reaction, tells you this reactant's name is an alcohol, goes to acetone plus hydrogen, and it tells you that the reaction is endothermic, that it has a positive delta H. So that's the same thing as saying heat would be a reactant. So I'd add heat to the reactant side if I thought about what this means. So the question is, does the amount of acetone increase, decrease, or remain the same when I make the following changes? So if we increase the temperature and heat is a reactant, Le Chatelet's principle says the reaction is going to go in such a way to decrease that added stress of heat, so it'll react forward. So we get more acetone, so it'll increase. If the volume increases, then we have one reactant and 2 products that are all gases. If the volume increases, that means pressure goes down. And if pressure goes down, Le Chatelet's principle says the reaction wants to go to increase that pressure, so to make more moles of gas. So it's going to react forward and therefore increase the quantity of acetone. When we add argon, that's a different way to change the pressure. Argon is not part of the reaction. So when we start out, we have three different species. So we have the total pressure is equal to the pressure of the alcohol plus the pressure of the acetone plus the pressure of hydrogen. Now when we change it by adding some argon, which is inert, we get the total pressure increases. The total pressure increases, but the important thing is the partial pressure of these species in the reaction don't change, because you could just cancel that from both sides. And so the total pressure of the reactants and products is the same. So when you change the pressure by adding an inert gas, there's no change in the reaction. You don't impact the partial pressures of the reactants. So there'll be no change in the quantity of acetone. D asks you what happens if you decrease, or when you add hydrogen. So if you add hydrogen, Le Chatelet's principle says it's going to want to go to the left to alleviate that stress. And so you'll decrease the acetone. And if you add a catalyst, remember a catalyst changes how fast you reach equilibrium, but it doesn't change where equilibrium is. So you should not change the quantity of acetone in that case. Okay, 97 is the last one I wanted to work on. It relates equilibrium to kinetics. So this is on page 533. We have this reaction shown at the top, which isn't particularly important. The important thing is, how do the rate constants change with temperature? So they tell you at two different temperatures what the rate constants for the forward reaction are and for the reverse reaction. So it says, is the reaction endothermic or exothermic, and explain using kinetics. So that means we want to explain using the rate constants, not the equilibrium constant. So the Arrhenius equation that we saw in the last chapter says a rate constant is equal to a pre-exponential factor times e to the minus EA over RT. If you just rearrange that to make it linear, so it's easier to think about mathematically, take the natural log of both sides, you get ln of k equals ln of a minus EA over RT. So that was shown to you in the last chapter. The reason I wanted to look at it this way is because this shows you that K changes with temperature, but the slope of that line is EA over R. So the larger the EA, the more the rate constant will change with temperature, because it'll have a larger slope. So if a reaction is exothermic, it looks like this, and the activation barrier forward is smaller than the activation barrier in the reverse. So I've written it here, the opposite. The reverse activation barrier is greater. Whereas if it's endothermic, the forward activation barrier is greater, because reactants go to products at a higher energy. Here, reactants go to products at a lower energy. And so if we can look at those, what we want to look at here is not what the values of K are, but how much they change with temperature. So when you look at this first one, 2.7 times 10 to the minus 9 divided by 9.1 times 10 to the minus 11. With that temperature change, it has changed a factor of 2.6. So this equals KF at 130 over KF at 1200. Okay, so that's the factor it increased. Now if we look at the K in reverse, 2.6 5 divided by 1.5 exponent 5. It has changed. Both of them have increased, you notice, but this one has not increased as much as this one. So the forward rate constant, or the forward rate constant is changing more. Therefore, who has the higher activation barrier? So I said that the slope is dependent, so the rate of change of the rate constant depends on the activation barrier. So that means the forward rate is changing more. So it looks like this guy, because the slope of the forward reaction is greater. Therefore, you can conclude that this reaction must be endothermic because of that. You could also, you could look at how, well, for this problem, I don't want to talk anymore because I want to make sure that you understand when it says explain using kinetics, you explain using rate constants and activation barriers. So you'll have another one that's similar where you'll look at what we know about how equilibrium constants change if they're endothermic or exothermic reactions. But for this one, I want to stop there to make sure that you understand that concept. So those are the problems. So enjoy doing your problems. And that's all I'm going to say for chapter 13.